Okay, let's see here. I mentioned we're collecting everybody back into the RDD, which is our class. And we'll get going here in a little bit. Let me try to boost the font size here. Okay, so this is the way that I would solve this. And I saw a lot of great approaches. But let's see. Do an RDD for README and do the word count for README. And then let's see here. I'll do the same thing off of changes. Word count for changes. And then join those two together. README join changelog. Oops, sorry. Wow, I messed that up, didn't I? WC, join WC. There. So let me put this back into the code here. WC and WC. I can go through this step by step. And actually, is that readable? Yeah, that looks pretty readable. Okay, so the first line there, what I did was to create an RDD. I call it RM for README. So it reads in the README file, creates an RDD, and then the next line is where I create a word count, flat map, and then split, filter, and then map to my word tuples and sum them up. Probably if I scoot this over a little bit, it's a bit more readable. Okay. Now, for the changelog, same thing. I created an RDD called CL, and then I do a word count on that and get those values out. Then at the last part, I take those two RDDs for the word counts, I join them together, and I show what the results look like at the end. Back over here, try this again. Back over here, the end results come out to an RDD that has, so we've got this tuple key value. The key is the string, the word. And then you've got this other tuple for the values. You've got the count from the left-hand side and the right-hand side, respectively, README and changelog. And it should come out with the results something like 12 and 101. So, sorry? Yeah, so that's a great question. So if you actually look at the intermediate values, the way that, if you're using _contains Spark, then you'll get some keywords that have Spark inside of it, but at the end of it, when the join happens, you're going to join the values that just have Spark, that exact string, as the key. And it depends. You could do contains, you could do equals equals. The way that I had the logic defined, I think I used equals equals. Yeah, I did. So I did _= Spark. So I was filtering out everything else way up in the pipeline. I could have done a contains there instead, in which case I get other keywords that contain Spark but didn't equal it. But at the end of the day, by the time you do the join, you'll come back hopefully with this tuple there that's just Spark and has a 12 on one side and a 101 on the other. Well, I mean, if you segment it this way, yes, that's all the keywords that contain Spark. So, yeah, so one of the troubles is this logic could be expressed in several different ways. You could do it in different orders. Hopefully, you'll get the same numeric results at the end. But if you look at the intermediate values, they will be different in between. The question is how much processing is happening in the intermediate. Quick question.
Yeah, that's a design question.
Yeah, yeah. It's. I mean it. Yeah, and it depends. Yeah, That's a great point. This is really a design question of how you want to build your app, what your business logic is going to be. It might be that you need to parameterize this and not just go after one keyword, Spark, but do other things. You may have other reuses for the intermediate values, so you could restructure this in different ways. But the main thing here is we just want to get through taking some earlier code, some earlier programs, and composing them together into a more complicated workflow that involved a join, because that's typically what you do with big data. You see this exercise of coming up with filters and joins over and over. Question?
So looking for instance, now you found many more than just join the two maps that kind of came out of it. So by default, anything that's a map structure, joins works on. He just says the key is good enough.
Yeah, exactly. So the question was that, really we just had a couple of maps coming out of this, out of the filter, out of the word counts. We had a couple of maps, and they're organized in key value pairs, and anything that comes out in that format, you could join. Yeah. So it's very nice because you could get these from different types of operations, but then join just by having that simple key. Question? Great question. So the question was, what parts of this are Spark and what parts of this is Scala? And actually, the way that this program works, almost all of this is Spark. There's really not a lot of Scala going on other than what's inside of the closures. So for instance, here we do sc.textfile, that's Spark API. Flat map is Spark. Inside of the flat map, the closure in there, where we say L goes to L split, that's a Scala expression. And the same thing inside the filter, the closure inside the filter, where we say underscore equals Spark. Again, that's a Scala-ism. If you were doing it in Python or Java, there'd be something different inside the closure.
It's just the lambda would be different.
Yeah, the lambda would be different. The anonymous function here. Yeah. But the function calls here are all Spark. I guess other than split. Good stuff. Any other questions on that? A number of folks asked about what time lunch would be. From what I understand, lunch is at 12. And that's important because some of us have to check out before 1. So definitely we'll take a long break well before 1 o'clock. If you need to check out, we'll be sensitive about that. All right. Let's go into a lecture here. Yeah, I can scoot through that. I want to shift over into doing a bit of a lecture about where this came from and what the motivations for Spark are, more from, say, a theoretical side, conceptual side. And I'd like to illustrate that in terms of starting with a timeline. If you look at the original papers about Google, the original MapReduce paper from Google, Jeff Dean and all, that work on MapReduce is being done in about 2002. And it was published for a conference in 2004. And subsequently that got picked up. Doug Cutting and others were working on the Nudge project as an open source web crawler. And out of the Nudge project, Lucene is one of the projects that came out. They were building text indexes, and they wanted to use MapReduce to build the text indexes. So that's where the Hadoop project got started. That was adopted, that work was like 2005, going into 2006. And then later it got adopted by Yahoo. By the time that 2008 rolled around, we were starting, I think that was the first or second, but it was the first Hadoop summit where there were a lot of other parties involved, other sponsors. Now, along this timeline, Spark comes in, really it dates back to, Matei can correct me, but I believe there was a skiing trip over one of the breaks in 2009. Spark dates back to 2009, but one of the first papers there was in 2010. And then rolling the clock up to 2014, Spark went through the Apache incubator process, became top level at Apache earlier this year, and subsequently made like record progress in reaching the 1.0 release status. It was a very, very quick process. What I want to illustrate here, though, is that MapReduce, again, dates back more than a decade ago, back to 2002. So our notions of Hadoop were really leveraging what kind of resources were available back then in terms of taking advantage of clusters of commodity hardware to be able to do fault-tolerant batch jobs. And a lot of the rhyme and reason of MapReduce was exactly that. Leverage functional programming, but take into account the fact that you're running on top of spinny disks and they fail at a certain rate. You want to try to maximize throughput for batch jobs. So, you know, MapReduce was this fault-tolerant framework that would allow a large-scale job to run with guarantees that it would complete and still be able to get away with using commodity hardware. What was commodity at the time? There's a great anecdote about this. If you ever read some of the, if you ever watch some of the videos about the early days of MapReduce at Google, Jeff Dean had one from, I think it was like 2011 Google I/O, where he talks about they had deployed MapReduce, they had deployed an app in production, and they were watching one day, and the app was running like 30% slower. Has anybody seen this video? Yeah, I can try to dig up a link, but it's hilarious because they noticed that this huge MapReduce job was running, but it was slower. And they called down to the data center, and they found out that actually the racks were being replaced. So the ops team was going in and powering down a rack at a time, swapping in new hardware, powering it back up. And MapReduce still marched right along, and the app completed just a lot slower. But it sort of points to the fact that it was built for fault tolerance. And it really worked in that case. So hopefully you don't have to swap out your data center while you're running your jobs. Now, the point I want to make here is that Spark is coming, about a decade later. And the reality of what we have in data centers is much different now. There are different kinds of issues, different kinds of things to take advantage of. But it's still this notion of applying really functional programming to how do we get the best results out of clusters of commodity hardware. If you want to look at some primary resources, I tried to pull back some of the papers on the history of Hadoop, some different milestones along the way. But as I said, data centers have really changed. If you look back at 2002, we had a very different set of things to work with. We certainly we weren't looking at having SSDs, for instance. We weren't looking at having really large memory spaces. Gigabit networking certainly was not there. Multi-core processors. None of that would have been, none of that would have been available, but none of it certainly would have been commodity hardware. And so the economics of data centers have changed. Spinny disks haven't changed all that much, actually. Memory is getting much cheaper, but the disks still kind of fail at the same rate and have similar throughput. So in terms of working with MapReduce, there were a couple of limitations that came out right away. We definitely saw this circa, on the Nudge project, circa 2005, 2006, even before Hadoop was starting to get a name. People were looking at early use cases and seeing that there are a couple things. One is it's difficult to get a lot of people thinking in terms of MapReduce paradigm and writing code directly in a MapReduce API. And I've seen that on my teams before. We've written a lot of Hadoop code directly to MapReduce API, and it was difficult to bring in people and get them to think about complex apps that way. So that's a conceptual level. The other side of it has to do with performance bottlenecks. And you can do a lot in batch, but it may not fit the kind of use case you want. I've seen over the years where people are trying to shrink down batch windows to get closer and closer to streaming in real time. And clearly, there's diminishing returns when you try to shrink batch windows. There's other problems in terms of asymmetries, key value asymmetries, and how processing in MapReduce apps can have bottlenecks. We can go into that in much more detail. But at the end of the day, MapReduce doesn't really compose well for more complex kinds of business logic, more larger kinds of apps. As a result, people spent a lot of time over the past decade building more specialized systems. And really, this comes out of a paper this is redrawn from something that Matei had shown in the last Spark Summit. And there's a great video from, if you didn't catch this, there's a YouTube video that we have up on the Spark Summit site. We started out with MapReduce, great for general batch processing, but then other kinds of specialized systems evolved. And a lot of this sort of followed the pattern of, maybe Google publishing a paper and then other people making an open source implementation, which which had happened with MapReduce and Hadoop to begin with. So you see things like Pregel going into Giraffe, or Dremel going into Drill, F1 going into Impala, Millwheel, etc. And what that led to was a propensity for a lot of different types of specialized systems, not exactly the same as MapReduce. If you're building apps that combine these, there's a lot of overhead in terms of the ops, the equipment, but also conceptually. A couple of great papers here in terms of history of Spark. Here's a paper from Usenix 2010, really the first formal paper about Spark. And then 2012, the RDD paper, which goes into much more detail about what we're thinking about today as Spark. So the thesis there was to generalize MapReduce, understanding that MapReduce had a couple of problems. Number one, the sort of conceptual bottleneck, if you will, of how difficult it is to express complex logic directly. And then number two, the performance bottlenecks of where you can really get in trouble with complex workflows. Both of those can be resolved to some extent with a couple of changes. And you know, I've seen that in the industry where there's a lot of good cause for using functional programming for big data. We can go into that in more detail. But the two changes that went into place here were to say, number one, fast data sharing, leveraging caches in a very smart way. And number two, having a general graph, a directed acyclic graph to represent the business logic of your app and then be able to have the lazy evaluation on it. So if you put those two together, you get the notion of an RDD as sort of this base abstraction in Spark, the caching and the DAG. And that allows an underlying engine to handle a lot of these different special use cases, all with the same engine, and in many cases with the same code, just with slightly different contexts. So, you know, we see proof in the pudding here where if you compare the code base, it's interesting, just as a metric, to take a look at the amount of lines of code in terms of the MapReduce API for Hadoop, certain number of lines, getting the streaming function out of something like Storm, certain number of lines, looking at SQL implementation like Impala, looking at Giraffe. If you compare that, though, with what's in Spark, just off of the basis of RDDs and all in Spark, and then adding these other libraries for streaming and graph, et cetera, it's about a 7-to-1 ratio in terms of the amount of code. And, you know, putting my engineering director hat on, you see this over time with teams. The more code you have, the more bugs you're going to have to fix, and the more code you're going to have to maintain. So there's a great value to be able to express a wide variety of different use cases, a wide variety of feature sets with Spark as a very general, uniform kind of engine underneath in much less lines of code. So some key points about Spark. You know, this has been covered in a lot of detail. I'm just going to touch on some of the high points. But definitely it handles batch, interactive, real-time, all within a single framework. You know, that should be updated to talk about machine learning and SQL, et cetera. There's native integration with Java, with Python, with Scala, now with SQL, work in progress on R. I heard yesterday about a project involving Clojure. So there's a Clojure DSL as well. I think it's called Flambeau. What this allows is programming at a higher level of abstraction. So we like to think in terms of abstraction layers where you have this kind of separation of concerns. You're thinking at a higher level of abstraction, expressing your business logic, building your workflows, and then a separation of concerns where Spark is doing the query planning and the compiler is doing something smart underneath that to obtain a lot more parallelism. That's really where a lot of the functional programming comes in, is to be able to express fairly simple expressions of transformations on your RDDs. That's your business logic. It's easy to troubleshoot, easy for other teams to pick up the code and work with it, but yet it's very powerful in terms of what's happening under the hood. And another thing is that, you know, MapReduce is just one set of the supported constructs. There's other types of things that are being done. In the general case, we're talking about the closures being combinators and being able to compose functions together, compose the combinators. This all goes back to like Alonzo Church and lambda calculus back in the 30s. but it's functional programming. A bit more practical, though, the RDDs are, there's really two aspects there. The lineage is being used on the one hand for fault tolerance, on the other hand for parallelism, and ultimately it gives you this pipelining effect. So, I talked about this briefly before, but the idea is you've got a base RDD that defines where do you get the data from, and then you apply different successive transformations to come up with these other RDDs. Nothing really happens until you have an action that needs to be taken. And by virtue of that, what that means is we've constructed this graph. We've constructed a lineage to express our business logic. And so if one node gets lost out in the cluster, you can pick up the base RDD again from a neighboring node that has a copy of that partition of the data. And then just for that partition of the data, rerun the graph, reevaluate the transforms. And so that gives you fault tolerance. But also built into that is your parallelism, because now you're talking about running this graph on different partitions of data and all running independently. Another thing that it buys is a very nice graceful degradation between taking advantage of all the RAM you have. If you can fit the working set of what you need to operate on all in memory, great, it will do that. And if you can't, then there'll be evictions. The different partitions in cache are being handled with an LRU, so it will evict the data that's not being referenced. And there's a graceful degradation to the point where you're not using any cache, you're just chunking through the data, doing spills out to local disk. But again, we do this in Hadoop, in MapReduce applications. We do this much more explicitly. With Spark, this is built in at a higher level of abstraction. You can parameterize it too if you want to control it. Okay, that's a lecture that I would have had to get up to the break. And we're at 11:45 right now. Let's see what we've got here. Spark Essentials. Let's go ahead. I'll go through a little bit more of the material, and let's see. Whenever we get the lunch delivered, we'll go to that early because I know a lot of people do want to check out. And there's the 1 p.m. Hard stop on that. So if anybody in the back, if one of the TAs, if you could check on whenever lunch comes, just signal. No, oh, great. Awesome. Awesome. Okay, so let's do a little bit more work here. I will talk a bit about some examples in both Scala and Python. Actually, before I go into this, any questions about sort of the theory of RDDs and how this differentiates from MapReduce? Yeah. That's a really good analogy. The question was, is it like journaling but for tasks? For the computation side, yes, it's very much like that. And you see that, sort of the borderlands on that is when you look at Tachyon and how Tachyon replays. Other questions? Yes?
Where's the lineage stored?
Well, the lineage, that is your graph. So the question is, where is the lineage stored? So on the driver, when you run the app, you're developing that graph. And then that's being serialized out and executed on the cluster. So essentially, the driver side of it is where that's being stored. Somebody knows that this program must be executed. Question?
So does that mean that driver failure is more catastrophic?
Yeah, that's a good point. Where it's starting out from, yeah, a driver would be much more catastrophic than having a worker node. Now, I've seen, depending on the kind of cluster manager, there's ways to get high availability on the jobs that are being submitted. It really depends what type of cluster manager you have. If you're working with Mesos, for instance, and you have a meta framework, then you can have high availability on the executors and then be able to run like Kronos in high availability mode for having no single point of failure on scheduling. So there's some different ways to go about that, but it really depends on what sort of cluster manager. Question?
Somebody asked it before, so what's the difference between like a Hadoop RDD compared to a distributed frame RDD, that kind of stuff?
Great Great question. So what's the difference between, we've seen different flavors of RDDs. What's the difference between them? I mean, there's a notion of an RDD, and there are certain types of functions that can operate on that, and that's in common for all of them. But when we start out with a base RDD, there's a couple different flavors. One is we can say that we take data from a collection. So if it's a collection in Scala, an array of integers, and we could parallelize that into an RDD. Alternatively, we could specify a URL or a path for a file. It could be, it could be something on local disk. It could be out of S3. It could be HDFS, et cetera. But in that case, we're creating the RDD directly out of the file. So those are a couple different flavors. In practice, though, once it's an RDD, you can do the same kinds of transformations on it. We'll see other ones like this, too. I mean, another case would be a schema RDD, where you take the result set from a SQL query, and then that can be operated on as an RDD. Question?
Yeah, instead of doing replay or batches for HA, can you do instead redundant computation? Discard duplicates?
Redundant computation, instead of replay. Well, trying to think of good examples for that. I'd love to drill down on that a bit more and figure out. I'll try to come up with some good ones for there. But
That's what virtually every streaming application does.
so you're saying the streaming applications virtually all will do recomputation. Okay, like the one-time only semantics off of, say, Spark. For one-time only semantics off of Spark streaming versus what you would do with Storm. Would that be an example, do you mean? Kind of. Oh, CEP kind of stuff. I mean, the replay really is, in a way, recomputing, if I'm understanding that right. So it seems like they're analogous. Does the Spark scheduler support? Well, I mean, that'll happen per node. I mean, it'll be happening per partition of data. So it really depends a lot on what's happening out there, or whether or not, like if a node gets lost, or if there's an eviction. Okay. Am I answering that right? Well, we'll take it offline. Let's catch up a little bit over lunch. Yeah, question? Yeah, we'll catch up on that. Any other questions along these lines here? Okay. Main point there, really 2 points. Number one, MapReduce came out of functional programming, and Spark does as well. Spark is more of a generalization of what you're doing, not just maps and reduces. And number two, this notion of RDD is really the basis of it. And there are two parts of that generalization. One is the caching, and the other is the graph. Alrighty. I'm tempted to say not even go into the next step, because we're coming up pretty much on lunch. Anybody know if we've got lunch yet? Oh, another question, yeah. Great question. So how do we compare Spark streaming with Storm? The notion of Storm, you can get the tuples being presented more than once. So one of the benefits on Spark streaming is that you get these one-time only semantics. You know that if you're seeing a piece of data, you're going to see that exactly once. Whereas with Storm, by default, you'd have to manage that. You could put Trident over the top of it or so. Another part where they're distinguished is that with Spark, you can run the same kind of code, business logic, in batch or iterative, interactive, et cetera, but also run it in streaming. So it's nice to be able to have the business logic reuse across different contexts. And I've definitely seen cases for that, where you have a lot of historic data that you want to run some kind of roll-ups on, or some kind of analysis, but then you also want to take a look at the most recent results coming off the web servers, and then be able to blend the two. So being able to reuse the same business logic in two different contexts is pretty powerful. Does that answer it? Okay, good stuff. Any other questions? You know, we're up at like 11:53, so I think that rather than jump into the next part of the material, Why don't we just call it good for lunch? And that way, especially if people have to check out, you've got some more time. And we'll re-adjourn here. It's 11:53 now, so let's say we'll come back in about an hour, a little bit over. Sound good? Great. I'll stick around if I can help out, answer with any questions.